Hey everyone, welcome to my talk. As Mitra mentioned, my name is Nasko Oskov, and I wanted to share today with you why running the latest version of the browser is critical. And just a little bit of background about me, but let me start off with thanking the FinJS organizers for inviting me to share some of my knowledge and experience with everyone here. And I would have loved to be with everyone in the same room, but I'm happy to at least have the ability to be having a virtual meeting with you all. I have been an engineer on the Chrome browser for about 9 years, coming up on 9 years now, and I've worked on security architecture, its process model, and subsystems like navigation, and many others. In my day-to-day work, I wear many hats. I'm an engineer. I am a security reviewer for a lot of the features that launch in the browser, and I also manage the Chrome security architecture team. So let me start off by establishing a baseline of what I'm gonna use today. While I'll usually be saying the word browser in the rest of this talk, what I actually mean is any product that is based on a browser code base. Examples of that might be frameworks such as Electron and the Chromium Embedded Framework, platforms like OpenFin, and many more. So when I say browser, it generalizes to any product that brings the web platform along with it. And why are updates important? There's many reasons. Some are new features. We add new APIs. There's also performance improvements. However, in this talk today, what I want to focus on is the security aspect of updating and why it's critical to be running the latest version. So in this day and age, security is actually very important. Our lives are mostly online. We use computer for almost anything that we do day to day. We even carry these small computers in our pockets called cell phones. And what is interesting is that every product, there's not a single software product out there that hasn't had a security bug over its lifetime, right? They happen in every single product. And Chromium is a massive and very complex code base. And just to give you an example, basically an idea of how big it is, if we take a Chromium checkout and just run this command, it will give us the number of lines of only C++ in Java code. And about 5 days ago, I ran it and it gives us a number of 20 million lines of code. And you might say, well, there's comments and everything, so we can actually just simple exclusion of one-line comments, which is mostly the style used within the Chromium code base. And that will actually still give us 17.7 million lines of code. So this is huge code base. And this actually does not include at all some of the UI, the chipset Chrome that is written in HTML and JavaScript. So the number is anywhere between 20 and 17 million lines of code. But also, let me establish a little bit of background for those of you that might not be aware of the Chrome's multiprocess architecture. It will give us a baseline to talk about some of the data I will present a bit later. So Chrome is composed by multiple processes. We start off with the browser process, which runs in the context of the user, is all powerful and non-sandboxed. And then it creates a bunch of other processes that are useful for actually running the browser. Well, to load a web page, you have to go to the network. So we have a network process which allows us to communicate with the web and fetch resources. Once those resources are fetched, we give them to web renderer processes. This is where the HTML parser, the JavaScript runtime, everything runs. And this is what produces pixels that users can see. Well, those pixels get sent to a GPU process, which takes it and displays it to the user. And because Chrome has a bunch of extensions that you could install, we run those in separate, slightly more privileged renderer processes, and they're separated. And finally, there's other functions that we want to run in Chrome that we want to be sandboxed, but are not necessarily either renderers or extensions, and we run this in a utility process. And all of that ends up running on top of the operating system. So as you can see, it's fairly complex interaction between multiple processes with lots and lots of code. So it is no wonder that Chrome has its own share of security bugs. And speaking of security bugs, let's look at some data of what do we actually have. This is a graph that shows us the security bugs that we have per year. And this number combines bugs reported to us from external researchers, as well as bugs that we find internally using our own tools, such as Cluster Fuzz, for example, which is our cloud-based fuzzing infrastructure. And as you can see, we have on average about 1,000 security bugs per year. And while that's a lot and might be hard to reason about, we can break it down into milestones, which are how we ship Chrome source code, and it's easier to understand. So going by milestone, the average number of security bugs is per milestone is about 51, and the median is 49. So given that data, if we do a little bit of math, what we'll find that if there's 50 security bugs per milestone, and let's say you're using a browser that or your code base is about 5 releases behind, what that allows is to give the attackers about 250 bugs that can be used to target you. And that is a lot of attack surface. I wanted to also share a little bit about where our bugs are. Remember back to the multiprocess architecture, we have about 66% of our bugs are in the render process. This is the code that basically takes the web content, parses it, and runs the DOM and JavaScript engine. Browser process, which is the most privileged process of all, has about 13% of the security bugs, and the rest are in GPU network and plugins. So you can see that the render process, which runs a lot of the complex code, has a big portion of the security bugs. Now, these come from different types of issues. But what we're seeing in reality is that from our high severity bugs, most of them are actually memory safety issues. Biggest portion so far is just after freeze. There are heap problems, there's buffer overflows, and very, very few bugs are not memory safety. There's some logic errors. If you see at the top of the slide at about 1.7%, UXSS is 1.7%. And I'll mention UXSS a little bit later, but with site isolation, this bug class has pretty much disappeared. But let me also walk you through why, what is the timeline of a security bug, so we can understand a little bit better what is the risk we're exposing ourselves by going through and not updating our browsers. So we start off with a report. We either get it reported by our internal tooling or we get an external report. But that is how the lifetime of a security fix starts off with. We then have assigned it to a developer, they start looking at it, and once they have an idea how to fix it, the first change gets published into the code review tool that we have, which is publicly available to everyone. So once the first change is uploaded, it takes a few cycles of reviews before the change actually gets committed to the source code tree. And once it is committed to the source code tree, what we need to do is create a release of the software that we ship to users. And once we've created the release and we started put it on our update servers, not all users actually pick it up immediately. So there's also time between us releasing the binary to the time where most users have actually updated their browsers. And excuse me. And what this allows is this window of opportunity for an attacker from the moment they see the first change to the moment that the users have actually updated their software, that allows attackers to know of a security bug and try to exploit it. And we call this basically a end day window. And we've been working really, really hard to shorten this window of opportunity for attackers. We started off with about an average of 33 to 35 days between first change in deployment to users. We have driven that down to 15 days at this point in time. And let's talk a little bit about what the attackers' profiles that we want to discuss are. We'll start off with zero-day attackers. And zero-day attackers are the people that are super skilled, that exploit bugs that they have found themselves or they've sold to a vulnerability broker, like this example of Zerodium. And it might be a little bit too small, but if you can zoom in or go to their webpage, you would see that they pay for a full Chrome compromise, they would pay $500,000. So these attackers do exist. Most of us don't have to contend with them, but they are real. And as you can see, actually, in the last couple of weeks, we have patched a few zero-day bugs. So that attacker class is there, but it doesn't matter how quickly update. If they have a zero bug, they will exploit it, and that doesn't quite impact us. What we strive on the Chrome team is to patch these as quickly as possible and deploy fixes as quickly as possible. There's also the end-day attackers. And the end-day attackers are the ones that exploit known bugs within the window of opportunity that we talked about. This is an example of a company which has published blog posts about the process of how they go about reverse engineering our fixes and developing exploits. There's another case of another company that actually blogged about a bug because we accidentally fixed it while refactoring a lot of code. They couldn't use it anymore, so they just described it in a blog post. And it's not just attackers. Actually, these folks are on the edge security team, and they wanted to see how long it takes them to weaponize and write an exploit for a bug that was known already. And if you look at the tweet, it took them about 3 days on average. So if our window is in the month or 2-3 weeks, 3 days to develop gives you still a couple of weeks of opportunity to try to target real users. But let's not talk just about bugs. Let's talk about how we're actually improving security within the browser space. We do improvements continually in various ways. We improve security indicators, for example, in the UI. We strive to message more clearly to users what is the current security state. We add security features. An example would be how we do a password check at this time. But we also do architectural changes. And those are more fundamental changes to how the architecture of the browser works, how the components interact. And as an example of that, let me walk you through an example of site isolation. Now, remember back the picture of the multiple processes that we talked a little bit ago? This is what a page looks like today. So if you go to a basic news site, what you would see is something that looks as a unit to the users. However, under the hood, it can have multiple documents being composed as a single web page. There might be an embedded video, there might be an advertisement, the main title, the main content of the article, and all of that prior to site isolation was running in a single process. So what that means is that, say, you have an attacker exploit that render process. What that gives them is the ability to talk to the browser process and request the cookies for your online accounts. It can request all kinds of locally stored data. It basically had no restriction as to what it can do. And let me just give you a glimpse of what it looks under the hood. This is the structure of that entire page that I just showed you in terms of all the documents that are composing it. And there's too many of them. You're probably not going to be able to read all the domains that are serving data for it. But what is important is to see the sheer amount of security principles that are part of this page that can read any data from your browser if it gets exploited. So what we needed to do is make sure that this is no longer the case. And we made a small change called site isolation that gives us this picture. And what the color here represents is each domain now runs in its separate process. What that means is that we have taken the monolithic web page that used to be rendered by a single process, and we have broken it down such that each site runs separately. And what this allows us to do is actually get some security benefits. One is we use the operating system itself to help us enforce the security properties in the browser. The process as an operating system primitive is what the operating system guarantees us that is their unit of isolation. We put every process in a very tight sandbox that varies from platform to platform, but that allows us to reason that a single process dedicated to, let's say, google.com or facebook.com or any other process, you name it, when they request information from the browser process where all the state and high privilege stuff is, it allows us to actually do access checks. So when google.com, let's say, is compromised because a renderer was exploited by an attacker, and it asks, let's say, for the facebook.com cookies, then we will deny it. And every time that we notice a irregularity in the security state, we would actually terminate that renderer process with the high probability of taking the attacker down with it. It also is a very good defense against CPU microarchitectural issues. About 2 years ago or 3 years ago now, Spectre, Meltdown, and all of the follow-up issues that exist in our CPUs today were discovered. And what that meant is that code running in a single process could read its entire memory. And that is pretty bad for browsers, because what we do is we allow JavaScript to run in a process. But a lot of the same origin policy implementation used to live in that same process. Therefore, if you bring data from a different origin, what would happen is Spectre would allow you to read anything. So that meant that even if we had no bugs in the render process, just a fully functional, correct browser, that meant that web page could just read any memory cross origin. So this is where also site isolation helps, because we put every site in a separate process, and process so far has been a stable primitive that we could defend against even with Spectre. And remember back to the render bugs that we had that are a huge chunk of what we find? Well, the other benefit is that site isolation gives us is we protect against arbitrary code execution in any render process. And our goal is to assume that every process that runs a web page is exploited and try to build defenses from that point on. And at this point in time, all of these protections are covered by our vulnerability rewards program. So if people find bypasses to all of our security protections with site isolation, we'll reward them for it. And we've had some submissions, and we're looking if people find more. But so far, we're doing well. So in summary, the web platform is great. But what you should do is update your browsers and browser-based products actually continuously. It doesn't matter whether you're running Chrome, you're running Edge, or any other browser built on the Chromium framework, or you are running Electron or Chromium Embedder or OpenFin. It is really, really critical that you shorten the window of opportunity for an attacker, because we have evidence that they are publicly talking about exploiting end days. We're seeing evidence of people attacking with 0 days. So in general, it should be very much high priority for you to keep up to date. And also, browsers are just not fixing just bugs. We actually work really, really hard on adding security features or pushing the architecture to a point where it makes life of attackers as hard as we can make it. And we're pouring a ton of time and effort in trying to do clever things and to push the boundary on security as much as we can. And above all, we're hard at work to secure a platform that every one of you is building on top. And I'm personally very humbled to have the privilege to be working on securing something that a lot of folks around the world use. And with that, thank you very much.